Let's see, the sum Sn of the first n terms of a geometric sequence, okay, we know that it's a geometric, whose nth term is un, is given by Sn equals that. So they've given you the formula for Sn, and they have also told you that a is greater than 0. You guys know what it is like, right? When they give you these kinds of restrictions, you have to look at it like later on when you're giving the final answer for something about a, the value of a, right? So we'll keep that in mind and start with the question. So a, find an expression for un. Un, well, there are two ways through which you can find this, but since the part B says find the first term and the common ratio, we're just gonna find the generic method for un instead of finding the first term and ratio and then building the nth term formula. So what it is so Sn, you know that it is u1, the sum of terms from u1, u2, u3, blah blah blah, up to un minus 1 plus un, right? So Sn minus 1 is the sum of the first n minus 1 terms. So the first n minus 1 terms are the same, but you are short of one term, right? So if you subtract that from the first line, then you are left with this on the left, and then the others all cancel out, and then you are left with only un on the right hand side. So that is how you find un in a generic term. So as we know that so we know that Sn is 7 to the n minus 8 to the n over 7 to the n. So I'm just going to write that as it is. And then if you're trying to find Sn minus 1, it's not that difficult. Just plug in n minus 1 into n in the formula. So that is like 7 to the n minus 1 minus 8 to the n minus 1 over 7 to the n minus 1. You might want to, further simplify this, but I don't see a reason here right now. If they ask you to do that, you should be able to just by combining the fractions. But for now, let's leave it like that. Okay, part B. Find the first term and common ratio of the sequence. Now let's do this. So when you have the summations, the sum formula, sum expression, then the easiest way to find the first term and the common ratio, or if it's arithmetic, the first term and the common difference, is to plug in numbers 1 and 2, right? So u1 is essentially the same as s1 because this is the sum of the first term, right? So if you plug in 1 into n, that would be 7 minus a over 7. And then you have u1 plus u2, which is s2. And then you have 7 squared minus a squared over 7 squared. So that would be 49 minus a squared over 49. But bear in mind that this is u1 plus u2. So in order to find the common ratio r, you need u2 as an independent term, which you can find by subtracting the first term from the expression we just found. So this would be 49 minus a squared over 49, which is u1 plus u2, minus u1, which we found earlier. So if we combine these to simplify, then for the first term it's the same, but then for the second term we are multiplying 7 to both the numerator and denominator, right? So I'm just gonna do 49 minus 7a, but just be careful with the sign because there's a minus sign in between the fractions. In that case, you have to make sure that that minus sign applies to the whole of the numerator. So you have to, it's just better if you put brackets like that. So let's see. For easier algebra, it's always easier to just cancel things out whenever you can. evidently you can do that because 49 minus 49 is 0. So you're left with minus a squared plus 7a over 49. The numerator, you can take a out, right? And then you're left with this. So this is some algebra that you should be able to do without much difficulty, okay? And if you're looking for R, then that's U2 over U1, which we can write like, so that's my cat. But anyway, so you can cancel these things out, right? And then like this, and then we're left with just a over 7. Oh, nice. So we have found what we intended to find, right? So the first term, to summarize, is this, and R is this. Right, so now part C. Consider the sum to infinity of the sequence. Determine the values of A. Oh, I think this has to look like a variable A. It just looks like a word A. But anyway, determine the values of A such that the sum to infinity exists. Okay, so that means the sum to infinity converges. In other words, the terms in the sequence tend to 0, right? So towards the end, although there is no end, when n is very big, the terms are almost 0, very close to 0. So adding them onto the sum doesn't make much change, right? So that's the condition for the sum to infinity to exist, and you should remember the condition, because it will always come up in an infinite sum formula, infinite sum problem. So so you should remember that it is always when the common ratio is in between -1 and 1. That is, again, because that will make the terms in the sequence tend to 0. In this case, our R was a over 7. That's what we found. So we have this, but we can't finish like this. I warned you in the beginning that when you have restrictions given in the question, you have to be careful. So we were given that A is greater than 0, so we have to combine that with what we found. Okay, that's my cat again. So we are left with this. Okay, so find the sum to infinity when it exists. Okay, so we assume that the part I, the result of the part I, holds, right? And then the sum to infinity formula is just this, very simple, simpler than the nth sum to n terms, right? And then U1 is 7 minus a over 7, and then 1 minus a over 7. There are two ways you can go from here algebraically. One is to combine the two terms in the denominator and then see what you get. But I personally prefer getting rid of the fractions in fractions whenever I can. So I'm going to multiply 7 to both the numerator and denominator and see what happens, okay? So in the numerator, if you multiply 7, you're left with 7 minus a. And then in the denominator, if you multiply by 7, you are left with, again, 7 minus a. So that's 1. Because, just make sure that none of these are 0 or undefined. And that's true because we know that a is in between 0 and 7, which means a is not 7. So neither of the numerator or nor the denominator is 0. So we are left with a very simple answer as the sum to infinity, which is 1.